So first of all, there are lecture notes. So I can just, okay. So maybe I'll write the title of the lecture and then point you to the lecture notes. So this lecture will be about lifts of polytopes. And there are lecture notes online at this address. Okay, so there are the notes. The notes have actually lots of exercises. I'll mention today sort of at the end some suggested exercises sort of to reinforce concepts that we'll need for next time. The other thing I should say is that the set of abstracts I gave, they're remarkably optimistic. So there's no chance that we'll actually cover all the information in the abstracts, but everything is in the lecture notes. So we'll try to get far enough so that with the notes, if an ambitious person could complete the agenda. Okay, so I think this is it. Let's okay, so let's get started here. Okay, so our setting is going to be that we have a polytope in n dimensions, and we'd like to optimize linear function over this polytope. Okay, so if you don't remember or recall, I mean, a polytope is just the convex hull of a finite set of points, or equivalently, the intersection of a finite number of half spaces. Okay, okay, so we want to optimize over these things. This is sort of, the hallmark of mathematical programming. What are some examples of things we'd like to optimize over? So let me give two combinatorial polytopes that will play a role in everything we do. The first one is the TSP polytope. Okay, so this is the convex hull. It's the convex hull of indicator functions of tors, okay, in the complete graph. So we're looking at the complete graph on n vertices. So there are n choose 2 edges. We look at things which are the indicators of edge sets of tors. So x is the indicator of the edge set of a tor in the complete graph. Does the definition make sense? Right. Right. So makes sense. Indicates all the tors. Okay, this is one thing. The other polytope that will play a role is the cut polytope, which is very similar. It's exactly the same thing, except it will just be the indicator of all the edge sets given by cuts in the complete graph. Okay, so let's say the same thing. Choose 2. Okay. Okay, let's even here, let's maybe say it in mathematical notation, where xij is like this for some. So here, 1s is just a characteristic function of the set S. Here, let's see if we can get the board higher. Okay. For a subset of 1 to n. Okay. Okay, so here's 2 examples of 0, 1 polytopes. And okay, now it would be great if we could optimize over these things. So of course, suppose we're given, say, an input to the problem, which will just be so for the TSP polytope and the cut polytope, the natural inputs are just a graph with non-negative weights. So given some weight vector with non-negative weights like this, we could consider various optimizations. So for instance, if we look at this, okay, this is just, of course, this is the, this is just the min TSP value of, doesn't matter what the formal definition is, but you can figure out the cost of the the lowest weight traveling salesman tour according to the edge weights given by W, just by solving this optimization, right? You minimize over, I mean, it's by convexity. I mean, this is sort of, you realize this for one of the extreme points. So, okay, so this is really the, I mean, this is really the problem of solving traveling salesmen. And let me just mention, like, I mean, if you, for the cut polytope, you could think about, for instance, solving max cut, okay, in a similar way. Okay, so this is like the max cut value of this weight function W. Okay. So I hope that it doesn't come as too much of a surprise for everyone. You know, if you could optimize over these polytopes efficiently, you could do things like solve traveling salesman and max cut, and well, then P is equal to NP, and you can do lots of other things too. Okay, what's the reason that, you know, this doesn't, you know, one cannot prove P equals NP via this strategy? Well, these are very complicated polytopes. Okay, so they're, you know, I mean, they're very difficult for us to optimize over. We don't know if we can optimize over them or not. In particular, their combinatorial structure is quite complicated. Like, you know, this one has n factorial facets. This one has 2 to the n facets. Okay, so they're very complicated. But that doesn't necessarily stop us. So let me give now another example of a combinatorial polytope, which I guess at first glance also seems complicated. So this is just the cross polytope. So the set of all x in Rn, it's just the unit ball of the L1 norm. So okay. So here's another polytope. If you look at the, it's also actually pretty complicated. It has 2 to the n facets. Okay, so a facet, by the way, is a sort of a largest dimensional face of the polytope. So for a full dimensional polytope, yeah, it's just in n dimensions, it's an n minus 1 dimensional face. Okay, so this is also, I mean, if you say to me that, you know, well, these are complicated because they have exponentially many facets, and therefore, you know, interior point methods cannot generically optimize over them, you would say the same thing about this. But okay, but it's well known how to optimize over this polytope. And essentially the reason you can do it is because this polytope is the shadow of a much simpler polytope. Okay? So there's a picture in the lecture notes. I don't want to draw pictures. Like, I'll draw a picture, but it won't be, it's not like going to be a mathematically accurate picture. But, okay, it looks like there's my picture. Okay. I don't know if it's, okay, so it's not so helpful. But the claim is that, yeah, the claim is that this polytope is the shadow of a much simpler polytope. Okay, so what's the simpler polytope? Let's call it Q sub n. This will be the set of pairs in 2n dimensions, such that what? Okay, so the yi's are helping us out here. So they're going to be non-negative, and they should sum to 1. And yi here is just meant to represent the absolute value of xi. So the other constraint you will have here is that xi sits between minus yi and yi. Okay. So here's another polytope in 2n dimensions, and it should be not very hard to convince yourself that the cross polytope is just a projection of this polytope of q sub n to the x coordinates. Okay, so this is just the projection onto the x coordinates of this q sub n. Okay. But whereas this one has 2 to the n facets, there's actually some exercise just to show that. It's very simple to see that it really has 2 to the n independent facets. I mean, this one is quite simple. This is for all I. It has only, if you count the number of inequalities here, then here's n inequalities, and here's n inequalities, and here's n inequalities. So this one has number of facets of this Qn is at most 3n. Right? So we get some. You see what I'm saying? So it's like this is defined by 3n inequalities. Really nice. Projects to this much more complicated object. Okay. And what's the reason that this is nice? So we'll define it formally in a second. But if we have some simple polytope that linearly projects to our polytope, then if we can optimize upstairs over the simpler polytope, we can also do linear optimization downstairs. Right? So this is a way of getting, okay. So it's yeah. Okay. So let's define it, and then okay. So definition: a polytope Q in capital N dimensions, which is a bigger number of dimensions, is a lift of a polytope P in little n dimensions. If P is the, let's say it this way, is an affine image of Q. So what does affine mean? It just means that you take a, you might have some translation, and then you take a linear mapping downstairs. Okay, this is, you don't even need to really think about this, since basically without loss of generality, you could just assume that the projection. Okay, let me put without loss of generality in quotes. Whatever. You could just assume that the projection is always onto a subset of the coordinates. That it's just, you just ignore some of the coordinates just by taking your polytope upstairs, first applying some affine linear map so that you position it correctly over the polytope P, and then just getting rid of capital N minus little m coordinates. So okay, so without loss of generality, this is just coordinate projection. Where without loss of generality means if you apply a map upstairs. Okay. So this is the definition of a lift, and then let's define one more thing, a notion of a little bit of complexity for a polytope. Let's do it here. Okay, yeah, let's do it here. So let's define gamma of P. This is the definition. This is the number of facets of the polytope P. Okay, and if you think about P as being specified by a bunch of linear inequalities, this is just the minimal number of linear inequalities you need to specify P. Okay, and then we can define sort of this lifted version, which is the the minimum over all possible lifts of this gamma. Okay, so this is sort of the, here for instance, e.g., gamma of the cross polytope is 2 to the n, and we just saw that, on the other hand, if we allow ourselves to take a lift, then we can reduce it drastically. Right, so this is what to think about. And sort of just a simple fact is that if we can optimize over Q, then we can, where Q is the lift of P, then we can also optimize over P, right? And the idea is just that, right, suppose you want to solve, let's say, you want to solve the minimum over X in P of W inner product X. Then you can just write this as, maybe I'll use a different letter, Z. You can just write this as the optimization over Q for some lifted weight function. And of course, I mean, without loss, since we're doing coordinate projection, the lifted weight function will just be filling the rest of the coordinates with 0. So if you want to optimize over P, and but maybe P is very complicated, if you can write P as the projection of something simple, now you can still optimize over P, but doing something perhaps much nicer. Okay? And the one thing you need to sort of complete this picture is that, okay, so let's, okay. Is that interior point methods can do this linear optimization in time, which is, say, polynomial in this parameter gamma, in the number of facets. Okay, so this is sort of, okay, you have to be, I mean, let's not get into sort of specifics here about sort of like, you know, whether or not the inequalities are specified with irrational numbers, and then you have to be a little bit more precise. But the point is that, you know, if a polytope has a small number of facets, then interior point methods can do linear optimization of the polytope efficiently. So that makes this immediately a parameter of great interest, because this is saying, you know, I mean, if you know, basically, okay, so gamma p might be large, but since if we can optimize over lift and we can optimize over p, then okay, you know, sort of like, really we just require this quantity to be small in order to do optimization. Okay, okay, so that's the basic setup. So this is what we're going to study, at least in the first 2 lectures, lifts of polytopes. We saw one example where the lift really helps. Let's just do one more that's sort of slightly more non-trivial. So let me. Sorry, that was my first time. I didn't know I didn't want it to slam into the ceiling. So. Okay. Okay. So this is the basic setup. It's very simple. You have a polytope. You ask, is the polytope the shadow of a simpler polytope? And our measure of complexity is the number of facets. So the number of inequalities you need to define the polytope. Okay, so here's one more example, which is the permutahedron. Okay, which is, okay, so here's it's the convex Hall of all the permutations encoded in the following way. I1 up to In, such that these run through the numbers 1 to n. So such that this set I1 up to In is equal to 1 to n. Okay. So, you know, just as a, you know, just in case the notation didn't make any sense. Okay. And, you know, now I've started, I have to, okay. Okay. In fact, let's erase this. It was more of like it's the kind of thing that makes sense in real time, but then afterwards seems pointless. Okay, like, you know, in pi sub 3 is the convex Hall of these things, right? It's just a way of encoding permutations as a list of numbers. All right, let's erase that. Here's a known fact, which is, if you really want to get it precise, maybe slightly non-trivial, but okay, it's on Wikipedia, that this thing has 2 to the n minus 2 facets. Seems odd, is that true? Well, it's on Wikipedia, like I said. Okay, so this is, again, has a very large number of facets, but here's a very nice lift of this polytope. So let's represent a permutation sigma by the corresponding permutation matrix. Okay, so this is the permutation matrix. Which permutation matrix is an n by n 0, 1 matrix that has, where every row and every column has exactly 1, 1. Right? Probably people have seen this, so it's natural how this encodes a permutation. The position of the 1 in the ith column tells you where the element I goes in the permutation. Okay, so you can think about these, you know, okay, you can think about encoding permutations by such matrices. So does anybody see a linear map? Suppose we have, okay, so suppose we have this this matrix, you know, I don't know. Okay, everything else is a 0. This is encoding some permutation on 4 elements. 1 goes to 1, 2 goes to 3, 3 goes to 2, 4 goes to 4. Okay, that's the permutation. Is anybody, and the rest of the entries here are 0. Does anybody see a linear map that maps this family of matrices onto this representation of the permutations? So I take such a matrix, I want to map it. Now this is in n squared dimensions. I want to map it to n dimensions such that I get exactly, this representation of the permutation downstairs. What does it mean? I need to also, I need to lose some things. I need to go down to n dimensions. I see. Yeah, that seems like that should work, right? So what's the claim is just that, I'm just going to rewrite matrix multiplication. That was the correct thing to say. That if we just say take the first row and okay, we just multiply on the left by, that's probably a better way to say it, by 1 to n, this gives us the correct map. So you see here, this is the, to every row you apply this mapping, and then you so this gives you a, so basically if you take the convex Hall, okay, so the convex Hall of permutation matrices is a lift of the permutahedron. Okay, just need to. That was basically the argument, just to verify things there. And then the question you can ask is, why is the convex Hall of the permutation matrices somehow simpler than the permutahedron was? Why does it have a small gamma value? And that comes directly from the sort of the Birkhoff-von Neumann theorem, which says that the convex Hall of the permutation matrices is exactly the set of doubly stochastic matrices. So this is by Birkhoff-von Neumann. This is exactly all the doubly stochastic matrices. And the number of inequalities you need to specify the set of doubly stochastic matrices is exactly n squared, just that all the entries have to be non-negative. And you have a bunch of equalities. The row sums are 1, the column sums are 1, but the only inequalities, which are the ones that give you facets, are just that Mij is greater than or equal to 0 for all ij. Okay, so this shows, these two things taken together show that if we allow ourselves lifts, then we get again a significant reduction. So this is here we have a lift where you need only n squared inequalities to define the lift. Okay, and I'll say it more formally soon, but the important thing to note here is that, again, to specify doubly stochastic, you have 2n linear constraints, right? Every row sums to 1, every column sums to 1. But the only thing that matters when you count the number of facets is the number of inequalities. And here the number of inequalities is just n squared, just that the matrices have positive or non-negative entries. Okay, so this is another example, sort of somewhat more non-trivial, of how the complexity can go down significantly if we allow ourselves to use lifts. And interestingly, the correct answer here, at least asymptotically, is n log n. This is the result of Michel Gemens. The lower bound of n log n is in one of the exercises in the notes. The upper bound actually comes from optimal sorting networks. So from a sorting network of size n log n, Aitai-Komlos-Samaretti, you can give an n log n upper bound here, better than n squared. But, okay, so those are two examples. Now the motivation for the talk. So is basically in the late 80s, there's a story, right, where Mihalis Yannakakis was on I think it was the stock program committee, and a gentleman submitted a paper to the conference claiming that P is equal to NP, and the proof was that there's a linear program for the traveling salesman problem of size with only order n to the 6th constraints. So an n to the 6th size linear program. So it's a complicated specification. I guess Mihalis sat down, tried to sort out what's going on there, found the bug, in the analysis actually that this program did not capture the traveling salesman polytope. So when I say it was n to the 6 size, it's exactly in the framework here. It was a claimed lift of the traveling salesman polytope with n to the, sort of with n to the 6 constraints. So they found the bug, so they sent it back. It's probably not unusual. People are sending P equals NP and P not equals NP papers all the time to stock. But the gentleman was, I guess, very persistent. So in the next conference, he again submitted a paper with now with n to the 12th constraints. And I don't know. I don't know if probably I don't know if Mihalis is on the second PC, but I assume someone got the paper to him, and he again found a bug there. But partly to avoid having to spend any more of his time focusing on such issues, he asked himself, can I prove that actually no such linear program can capture the traveling salesman polytope? Which is, it's a remarkably ambitious question to even ask yourselves. We have very difficult problem. They have a very hard time to prove lower bounds on even kind of trivial models of computation. But this is a model of computation that captures huge swaths of linear programming, so that it's very so it's even ambitious to think to think about this question. But Mihalis did, and in fact, he didn't manage to prove that the traveling salesman polytope has no small lift, but he proved that it has no small symmetric lift. So there's some exercises on symmetric lifts, but let's not get into the definition. But at least this was enough to rule out these approaches by Swart, because all of his lifts were symmetric. I will note that, by the way. So I'll tell you that. So that was in like the late 80s. That was in 1988, 1989, and then so Mihalis proved that there's no symmetric lift of the traveling salesman polytope, and then there wasn't much sort of progress made in this area for 20, 25 years until recently. This paper people really know about, Fiorini. Zawari, and the Masari probably doesn't have a Y, and Ronald DeWolf in 2012. And what they proved is that for both TSP and the COD polytope, there's no small lift, symmetric or not. Okay, so they proved strong lower bounds on the lift size for TSP and the COD polytope, and so we want to. Our goal here in the next couple of lectures is to prove this using a method that will extend to not just to linear programs and polyhedral lifts, but to semi-definite programs. I bet they have to be greater than 1. Probably. That's a more impressive result, I agree. It's kind of, so it's a bit shocking to me. So let me say, I'll come back to this in a second. Let me say that, here the lifts we talked about, they just capture exact characterizations. But you can also talk about approximation. So I'm not going to talk about it, but again, there are some exercises dealing with the approximation framework here, which is the idea that so think about the setting of a lift, but now let's say so here's the, just very briefly, here's the approximation setup. Q is in n dimensions, P is in little n dimensions. We have an affine linear projection, and now we don't require that pi of Q is equal to P. We just require that it's a relaxation, so pi of Q is containing P. Okay, and then once you have this, you can ask, it's only a relaxation. How well does it do? So in terms of the sort of a problem we care about. So you would ask about, say, for maximization problems, here's the approximation question. You don't need to sort of think about this formally. Just right? You have a lift which is now relaxation, and then you ask, for the weight functions you care about, how, since it's a relaxation, this is always going to be bigger than this, but you can ask how close it will be. So this sets up a way of talking about approximation problems in this setup. And if you think about sort of all this together, this captures, I think I'm safe to say, 99%, for instance, of linear programming approaches to approximation algorithms for NP-hard problems. I mean, with a very small handful of exceptions, this captures them all. In particular, it captures all of the stuff that Eden's been talking about. All these lift and project systems are captured in this model. So it's like quite striking that one can prove lower bounds on a model that has so many sort of like, where you can write so many algorithms that actually do non-trivial things. And it's a beautiful model, right? It's just about projection. So I mean, somehow it has some. It feels like a canonical model. One of the things that like Eden's lectures were sort of like blue collar. Like, I mean, you really want to get your hands dirty and get some work done, but it's not clear. But there's like many different lift and project systems. There's a sort of maybe an existential crisis one has when you start to think about them. Am I reasoning about something real or just like some kind of human edifice on top of something else? But this is somehow this model is like very pleasing because it's sort of it's very pure. It's just about whether there's something upstairs that projects to you and is simple in this sense. Okay, I got sidetracked by philosophy, so let's come back. Let's see. Okay. What do we want to do now? Okay, good. So let me, so how does one do this? So how does one prove such lower bounds? Well, it goes back to Yannakakis and the method he used for symmetric lifts, which is based on non-negative matrix factorization. Okay, and somehow this connection is what allows you to prove non-trivial lower bounds, even on this very strong model, and it's a beautiful connection. So let's look at it. Okay, so now again, let's fix a polytope P, and and we can write a polytope in two different ways. Okay, so let's write P in two different ways. First of all, we can write it as a convex Hall of its vertices. So let's write it as a convex Hall of, say, this capital N is not the same as this capital N, so let's use a different letter, in fact. And little n is the dimension. I don't have so many letters in my repertoire. Okay, let's use T. Okay. So it's the convex Hall of its vertices, and we can also write it as the set of points satisfying a finite list of linear constraints. So we can also write it as a set of all x in Rn such that, let's say, ai x is at most bi for I from 1 to m. Okay, so we write the polytope in two different ways. And then, associated with these representations, we can define the slack matrix, which is the following. So it's indexed by, let's say the first index will be the constraint, and the second index will be the vertex. So it's indexed by inequalities and vertices. And here's the entry of the slack matrix. Okay, so here's the entry of the slack matrix. So what does it say? First of all, notice that all of these entries are non-negative. All the vertices, of course, sit inside the polytope, and all the points of the polytope satisfy these linear inequalities. So these are all non-negative. And what the slack matrix does is it captures sort of for every constraint and every vertex how much slack is left in this constraint. How close is this constraint to being tight for that vertex? Okay, so this is the slack matrix it's associated with the polytope P, but in particular, but it also depends on the representations we choose. Okay, so that's one thing we need. And the other definition we need to sort of state Yanakakis' factorization theorem is a definition of non-negative rank. Okay, so first let's remember the definition of the rank of a matrix. So the rank of a matrix M is the minimum R. Okay, let's see what are the dimensions of this matrix. This is a M by T matrix, M by T, good. Okay, so it's the minimum R so that we can write M as A times B, where A is M by R and B is R by T. Okay. That's the usual linear algebraic rank of a matrix over the reals, say. Okay. Everything is real, so that's why it's the rank over the reals. And okay, the non-negative rank is exactly the same thing, but since we have a non-negative matrix M, we can ask for something stronger. We'll ask that both of the factors are themselves non-negative matrices. That defines the non-negative rank. R, okay, so same thing, but now A is non-negative and B is non-negative. Okay, this is the definition of non-negative rank. It only makes sense, obviously, for non-negative matrices. It's a bit of a, cruel joke that sort of you can write it in such a similar way to the rank because it's very, very different. The rank is somehow a very nice quantity. The non-negative rank is like is very, very complicated combinatorially. For instance, I think even to determine if the non-negative rank of a matrix is equal to 3 is the NP hard. That sounds like it could be true. Okay, so this is a very kind of difficult parameter to get one's hands on. But now let me state here the factorization theorem. Okay, so this is from Yanakakis. And it says that for every polytope P, the minimum size of a lift of P is exactly the non-negative rank of the slack matrix M for any slack matrix of P. Right? So we could come up with different representations of P. We would get different slack matrices. It doesn't matter which one you use here. The non-negative rank of any slack matrix gives you precisely the size of the smallest lift for P. Okay. So what time? We started, when do we end? Okay, good. Does the statement make sense? It's a nice statement. Why? Okay, so so one of the exercises which I will suggest at the end of the day is actually to prove that for any two slack matrices of a polytope, they have the same non-negative rank. And if you do that exercise, then basically you see the proof of this. The proof is just Farkas's lemma. But let's hold off for a second on why this is true. And then we'll come back to it. Actually, let me say one thing about why it's true. So, right, you can think about a polytope as where's this? You had this nice little, I tried to imagine, like, while you were lecturing, if there's a way to wash part of the board so it dries off by the time you get there, but I couldn't figure out a policy that would work. So, Does this work as is? If I just... afterwards you use the squeegee. Okay, sorry. Oh, that's really nice. Okay, so yeah, you can think about a polytope as sort of, well, obviously as a collection of linear inequalities. What does Farkas-Lemma tell us? It says that every linear inequality which is valid for a polytope P can be written as a non-negative combination of the defining inequalities. Okay, so in some sense you can think about the defining inequalities as sort of, like suppose you want to prove an inequality that's valid over P. You can think about the defining inequalities as some sort of axioms. Like they define the polytope, those things you know are true. And then the rest of the inequalities that are valid for P are derived from the axioms just by taking non-negative combinations of them. So you can think about the non-negative combination as a proof of your inequality. And basically, it's very easy to interpret this non-negative rank as the smallest set of axioms you need to prove all the inequalities valid for P. And in fact, just sort of telling you that, now it's an exercise to prove it. Does the squeegee help? Sorry, I'm not. This is more sophisticated than most Blackboard systems I see. So it kind of helps. Am I supposed to have a bucket or something? If somebody, everyone's laughing, but I feel like I'm really just winging it here. I have no idea what's happening. Okay. 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 Good. So now, okay. So now we stated this theorem, and our goal is going to be. Our goal in these lectures is okay. The integrity of chalk decreases under being wet. Okay. Sorry, where were we? Okay, good. Okay, so our goal is going to be to prove a lower bound on, on the size of the smallest lift needed to capture the cut polytope. Although we want to do it in a way which is different from the way that Fiorini et al. Did it, because this way is going to sort of generalize considerably to, for instance, to the approximation model and also eventually to semi-definite programs. And the way we want to do it is actually by giving a connection between arbitrary lifts, which sort of this gamma bar parameter captures, and very specific canonical family of lifts that at least tangentially you guys have already seen, those coming from the Shirley-Adams hierarchy. So basically what we want to show, the plan is going to be to show that if there's a small lift of the cut polytope, then there must also be a lift of a very canonical form, which is essentially coming from Shirley-Adams hierarchy. And so then the problem of proving a lower bound just becomes proving a lower bound for Shirley-Adams, which is actually completely trivial just for the cut polytope. Okay? But the idea is just to show that, for the cut polytope, there's a canonical family of lifts that, given the size, given the number of inequalities you want, there's a best lift of that size. Okay? That's how we want to prove the lower bound. Okay, so this is our goal. So to do that, we should talk about what a slack matrix for the cut polytope looks like. And then for that purpose, it's nice to introduce something which is isomorphic, linearly isomorphic to the cut polytope, but looks slightly different. Okay, so this is the correlation polytope. It's the convex Hall of all of the matrices of the form X transpose, where where x is the element of the discrete cube. Okay, so it's sort of right. It's all of the rank 1 Boolean. It's the convex hull of rank 1 Boolean matrices. This is the correlation polytope. And here's an exercise, which is legitimately an exercise. It's written in the exercises, which is that that the cut polytope with parameter n plus 1 and the correlation polytope with parameter n are linearly isomorphic. Okay, so combinatorially, they're the same polytope. Okay. So that means that if I want to prove a lower bound here, I'll just focus on the correlation polytope. And now I want to see sort of, okay, what are the types of inequalities that are true for the correlation polytope? Okay, so for that, we need a couple definitions. Okay, so the first definition is that of a multilinear polynomial. So a polynomial P on Rn is multilinear. Well, if you know. Okay, so let's just write it. P of x1 up to xn. You know, if none of the monomials has a power of xi higher than 1, right? All the powers of xi are 0 or 1. So you can, in fact, write down exactly what the form of this thing is. Sum over all subsets, some coefficient. Okay. Okay. It's written like this. It's for some coefficients, it's the sum of monomials where, you know, every xi appears to power either 0 or 1. This is a multilinear polynomial. And now let's define the following class of polynomials. Okay, so quadratic, multilinear, and they're positive. So this is the family of all polynomials P, such that I'll give you an example in a second. P is multilinear. P is quadratic. So actually, yeah, say. This one, both of them. Okay. Is it good? Okay. Okay, so this is going to be the set of all polynomials that are multilinear, degree at most 2, and such that they're non-negative on the discrete cube. Okay. So let me give 2 examples of such things that will both appear in what we're talking about. So one example that we'll see. I mean, here, I'm just writing down. Okay, everybody can see what it means. But for instance, here's a quadratic multilinear polynomial, except that it's not. Okay, except it is if we. Okay, interesting. What's the best way to explain this? So the point is. Okay, so multiply out, and every time you see xi squared, replace it by xi, because we're thinking about things over 0, 1. Yeah. Okay. Does it make sense what I wrote here? This is a quadratic polynomial. Clearly, it has as a form of polynomial, it is not in fact multilinear. But if you replace xi by xi squared, it will be multilinear. Yeah, unfortunately, my other example suffers from exactly the same problem. Okay, but here's one example. I mean, take any quadratic polynomial, and just every time you see xi squared, replace it by xi. Then you get a multilinear polynomial. Over the discrete cube, it didn't matter whether we took, because xi equals xi squared on a discrete cube. So it's not really so important for us. But here's okay. What I claim is that the sort of the inequalities that are valid for the correlation polytope are exactly are exactly sort of the ones in this family. I'll say it in a specific sense, but the quadratic multilinear polynomials that are non-negative on the discrete cube are exactly the inequalities that are true over the correlation polytope. It's like the linear inequalities. Okay, so to see that, just take some linear inequality on the correlation polytope. Okay, so if we have a linear inequality, it's true, you know, for the whole polytope, if and only if it's true at the vertices. So just sort of examine what it might look like. Maybe something like, okay, so A0 is a constant, A is some constraint matrix. Here's a linear inequality. Well, here I've written it at one of the vertices, but okay, in general, we could just, you know, take some matrix M. Here's a linear inequality in n squared dimensions. If we write it down for the vertices of the correlation polytope, and then, you know, like, let's express this now. This is exactly saying that sum over all I not equal to j, ai j, xi, xj, plus maybe sum over I, maybe there should be a 2 here, of a I xi minus a0 is greater than or equal to 0. Okay? Here I just use the fact that for 0, 1, you know, xi squared equals xi. So this is, you know, this is the diagonal, so it was xi squared, but that's the same as xi over 0, 1. So I'm just saying, sort of like every linear inequality when we in n squared dimensions, when we evaluate it at a vertex, you see we get an inequality like this, which is just you know. So if it's true, that means that it's, you know, okay. So if it's true at all the vertices, right? Then this is true. And you see, this is just this exactly means that this defines a non-negative quadratic multilinear function on the, you know, on our end. Okay. So the point is the inequalities that are valid for the correlation polytope are exactly of the form f of x greater than or equal to 0, sort of for all okay, I don't know. Yeah. Okay, so sort of like okay. So every quadratic multilinear function which is in this class satisfies, you know, satisfies this. These give exactly all of the linear inequalities that are valid for the correlation polytope. So and also we see exactly what the vertices are for the correlation polytope. So the point is now we can just write down the slack matrix of the correlation polytope in the following way. It's indexed by functions that are quadratic multilinear non-negative and vertices. Let's put the index n here. And then it's just f of x. Okay. Here, f runs over this class of functions, x runs over. Okay. So I'm claiming that this is the this is precisely, I mean, a slack matrix for the correlation polytope. Okay. And it's just, again, because when you write out what the things are, you're just getting quadratic multilinear functions, the multilinearity coming from 0 squared equals 0 and 1 squared equals 1. Okay. So then if we this is very bad form to sort of go back in time and write something. But so then we can restate our goal as just to prove a lower bound on the non-negative rank of this matrix. Right? Okay. So you can see, I mean, already, everything we've done so far are equivalences, but somehow this feels like a much more tractable problem than proving that no polytope of small size can project to the cut polytope. Now it's just, I have a bunch of quadratic functions. Can I bound the non-negative rank of this? And I want to suggest the correct way to think about this problem of the non-negative rank of this matrix. So here's how we're going to do it. Let's say that R is equal to the rank of this matrix. And then let's, okay, so we know what it means. It means we have a factorization. Let me rewrite the factorization very slightly, just in the following way. And then it'll connect the things we talked about a moment ago. Okay. Okay, so AI here are the columns of the matrix A, and the B and the BIs are the rows of B, or vice versa, depending on how matrix multiplication works. But okay, so the AIs here are functions from our non-negative functions on quadratic multilinear functions, and the BIs are non-negative functions on the discrete cube. I just wrote down slightly differently the definition. I guess here I should have written it like this. So f of x equals the f comma x entry of this matrix. Now, if the matrix, which means that we can write this, if the rank is R, we can factor this matrix into A times B, and this is just rewriting the factorization slightly. So this is what it means to factor this matrix. That we can write f of x as a sum over R terms, one of them evaluated, everything non-negative, one of them evaluated f, one of them evaluated x. And so, and here's the correct way to think about this. We know that these functions f, like they're non-negative on 0, 1 to the n. Okay. So you can think about this like a proof system, where these are sort of the axioms of the proof system. I have a bunch of non-negative functions. So of course, if I take non-negative combinations of them, I get other non-negative functions. So these are sort of our axioms, and then sort of these coefficients represent the proof, right? So if I can write f of x as a non-negative combination of non-negative things, then that gives me a proof that f of x is itself non-negative. So now you see really what I said before is sort of like that's exactly what's going on here. The rank of this matrix is exactly the smallest family of axioms you need so that you can prove every quadratic multilinear inequality on the discrete cube. So it's so you're really just saying, okay, there are lots of inequalities there. I want to take a small family of functions, so a small basis, so that I can prove them all just by taking linear combinations of the things in the family. And then the question of non-negative rank is just, is there a compact family of axioms for these functions, which are, they're not so complicated. They're just these things. Okay. So that's the question. Okay, I wanted to take a break, but now it actually looks like we might finish the lecture. So I don't think we should take a break. We should power through. Okay, so this is the setup. We want to prove that we cannot find a small family of axioms that prove all of these inequalities. So you can start to think like what kind of axioms, okay, if you had to come up with a small family of axioms, what would they look like? And there's sort of a canonical family of things to look at because, okay, notice that like this matrix is very symmetric. I mean, if you, for instance, if you permute all the coordinates, then you permute the of 0, 1 of the hypercube, you permute the entries of this matrix, but the matrix, up to this permutation stays the same. So you might expect that your family of axioms should also be symmetric. I mean, I don't know. You're proving a family of statements that are symmetric. Maybe the axioms should also be symmetric. Okay. I don't know if it's. I mean, in this case, it happens to be true, but there's lots of open questions that would be solved if that was the case. So if you're thinking about symmetric families of axioms, but you also want them to be small, then there's actually a sort of a canonical set of axioms you might try. This happens to be the Shirali-Adams system, but we'll say it here in a very different way. Okay, so let's make a definition that a function g, a real-valued function on the hypercube, is a k-junta if the value of g depends only on k, so yeah, at most k coordinates. Okay, so it just means that there's at least n minus k coordinates where if I flip their value from 0 to 1 or vice versa, it doesn't affect the value of g. So there's some k coordinates, g is determined by its value on those k coordinates. Okay. Okay, so okay. Yeah, so then let's do, okay, so here's another part of the definition. What's the right way to do this? Sorry, I want to be consistent with the notes, but now I realize the notes made a poor choice. So now it's like there's some tension. Okay, so let's okay. So if we take the, okay, think about the cone of all of the k-juntas, okay? Okay, so these are functions. You can think about them as being vectors in a 2 to the n dimensional space, but but forget that. Don't think about them as vectors. Just think about all the non-negative combinations of k-juntas. Okay, and you can ask, how many elements? I want to say that the sort of like if we put k-juntas, if the bi's are k-juntas, take the bi's to be all possible k-juntas. I want to say that this is okay, I want to say that this is a small set of axioms. It might not prove all the things you want to prove, but it's a small set of axioms. So, okay, so basically my question is how many functions do we need to generate all of the non-negative combinations of okay, and here I only want to take non-negative k-juntas. Yeah, so how many functions do we need to generate the cone of all non-negative k-juntas? This is just a set of all functions that can be written as non-negative combinations of things that only depend on k coordinates. So I want to write it as the cone of something nicer, okay, which is what I'll call j sub k. And okay, so I'll just answering the question. So this will be the cone generated. Okay, so this is the same thing as the cone generated by the following functions. Okay, so you go over all set to size at most k, and all z, which are sort of bit strings in S. And let me just put down here the definition of this function. So when I look at this function at the value x, it's 1 if the restriction of x to the bits in S is equal to z and 0 otherwise. Okay. So this function is just look at the bit, take a subset of bits, look at the bits in that subset. Do they equal the pattern given by z? Okay. That's this family of functions. Okay. And I just claim that these functions generate the entire cone of k-juntas. Of non-negative k-juntas. This is also an exercise, but isn't it obvious? Yeah. You can just take any k-junta and just write it as a sum. Just write it as a sum over delta functions of, does it equal this value? Like a k-junta depends on k bits, so I can just write it as a sum. Does it equal this value on k bits? Then I multiply it times the correct value. Does it equal this value on k bits? I multiply it times the correct value. So you can write, okay, so we'll leave it as an exercise, but you can take any non-negative k-junta and just write it as a sum of 2 to the k of these functions. Oh, okay, just as delta functions. Okay, so the point is that, okay, so like this cone has is spanned by only, I guess then we should say one more thing here, which is that the size of this set is at most n to the k. Okay, and so what I want to do is consider, sort of, we said we're looking to see if a small set of axioms can prove that all of these quadratic multilinear functions are indeed non-negative. I'm giving a proposed set of axioms that's very simple, which is just take all the k juntas. So the bi's can be every possible k junta. And I'm saying this is not an infinite family of functions, because actually you can get them all with just n to the k rays. This cone is generated by these rays. Okay, good. So you can, so this is one potential family of axioms. This exactly corresponds, this family of axioms exactly corresponds to the k-round Shirali-Adams lift of the cut polytope. You don't need to know that, but it's true. Okay, and I sort of, it's like, yeah. So this is sort of what I would call a canonical family of axioms that you might try to use. And they're symmetric, right? If you permute the coordinates, the family JK doesn't change, and because they're juntas, I mean, the number of them is only n choose k. Well, order n to the k. And in fact, you can prove that if you take basically, if you take a family of axioms of size about n to the k that's symmetric, then everything they can prove can be proved by k juntas. So sort of these are universally, among all symmetric families of axioms of size about n to the k, these are the most powerful. These are some of the reasons addressing, for instance, in one of your questions today about sort of like, why Shirali-Adams is nicer than these other systems. I mean, kind of, again, it kind of comes from God, as opposed to sort of, if you say you want symmetric axioms and you don't want too many, you get Shirali-Adams. Okay, we're almost done. I just want to state the theorem they will prove next time. So, good. Okay, so this gives our sort of and I want to introduce some notation that will make it so that we don't have to review anything next time, except for the definition of this matrix. So if I give you a function which is non-negative, I can ask you about sort of what's the smallest value of k so that you can prove the non-negativity of that function using k juntas. Right? So what's the minimum k such that f lies in the cone generated by the k juntas? And in fact, now we can just, let's define it. Let's define that as the junta degree of the function. So I have a function, I define its degree in this junta sense as the minimum value of k such that f lies in the cone generated by k juntas. And easy fact is, well, it's at most n, because every function is itself an n junta. It depends on n coordinates, so that's fine. So now let's finish by just stating the theorem we're going to prove next time. I mean, next time we'll also show that these things do not suffice so to prove this theorem. So we'll show that there exists, in fact, we wrote it down. Yeah, the example, for instance, has junta degree n. and no smaller. So you cannot prove that that thing is non-negative using n minus 1 juntas. There's no way to write that function as a non-negative combination of non-negative functions, each of which depends on only n minus 1 coordinates. And it's the easy. That's really easy exercise. You could prove that in. Okay, maybe we'll make it an exercise. Good. Okay. Okay. So, but the theorem is now that actually proving lower bounds on the Junta degree is all that's necessary to prove lower bounds on the non-negative rank. Okay, so this is from joint work with Suan Chan, Prasad Raghavendra, and David Storer. This is the following. Okay. So for every function g, okay, g is non-negative, and it's a function on, this is an m, so it's a function on m bits. And every n, let's say it's at least 2m, the following is true. The rank, the non-negative rank of mn, okay, which is sort of this matrix, which is all the non-negative quadratic functions on the hypercube evaluated at the points of the hypercube, is at least, okay, I have to, okay, for every g, okay, I'll just write it this way. Some constant depending on g times n to the degree, to the Junta degree of g minus 1. Okay, this is the theorem. And it's for, okay, so you give me any function, okay, which is, let's say, we want it to have large Junta degree. Then the claim is that for all large enough, okay, this is true what I wrote here. Yeah. This is true. Yes, it is true. Yeah. The claim is that for all large enough m, the non-negative rank is lower bounded by n to the degree of g. Okay, with a constant that depends on g. Okay, so if you can, if we can prove a lower bound on the degree of g, say if we can just find, say, quadratic multilinear. I should say, this thing has to be one of the things we talked about. It has to be a quadratic multilinear function. So if you can find a sequence of quadratic multilinear functions whose degrees are going to infinity, at least it will prove that the non-negative rank of these matrices cannot be bounded by any polynomial. Just because for every fixed exponent, you'll find a g which has large Junta degree, and you'll plug it in here and get something that grows faster than that. And that, via the connection, via the factorization theorem, that gives you, that at least shows you that super polynomial lower bounds on the size of Lift's sublacat polytope. Okay. So this is what we'll prove next time. And yeah, I mean, this is capable of proving much stronger lower bounds, but in the form I stated here, the fact that the constant depends on, okay, so this is some, this is some constant c of g, which depends in some arbitrary way on g. So at the moment, you can only apply it, you can only apply it for fixed g. If you want something stronger, you have to be more careful so that you can, and actually figure out what this constant is. But this is our goal for next time. And if you think about what it's saying, you can restate it as saying, in the contrapositive, if there were a small family of Shirali-Adams relaxations for this family, so if these degrees were small, like if you could do every one of these things with constant degree, then it would imply, sorry, I went the wrong way in the contrapositive, sorry. I should say, if there's a small lift of this polytope, it would imply actually that there's, that these degrees, like if there's a lift of size n to the 10th, it will imply that these degrees are uniformly bounded by 10, which means there's actually a small Shirali-Adams lift of the same family of polytopes. So this theorem encodes the fact that if you have a small lift, actually there must exist some other lift which is of a very, very canonical form and is also small. Okay, let me stop there. Thanks.